Hello everyone. Welcome to this Hello everyone. Welcome to this new video where we are going to go through maximum difference between node and ancestor. So basically what we have here, we have a tree and we are supposed to find out what is the maximum value we can have looping through the element and find the difference between every node and its ancestor. So let's say for instance 8, you are going to try to compute the difference between this and all its like children and find out which one is the maximum value. Do the same here and find out which one is the maximum value. And don't forget that it's not just about the root and the other one. You need to do the same for any subtree. So let us just find out exactly what it means. Let's say we have this node, for instance, like this tree, for instance. This is a possible difference, like 8 and 3. 3 and 7 is also a possible difference, 3 and 7, because this is actually an ancestor of this. So you have a lot of possible combination. So in this program, we are going to see two approaches. The first one is actually the direct implementation of what I've been described here, and we are going to see what is the missing part of implementing it that way, and we are going to correct it and find a more optimal solution for this. So now that we are fully aware of how the thing is supposed to work, the next thing I'm going to dive in is the approach of solving this. So my first approach of solving this will be, okay, I will say for each road you are going to the solution of the system is actually equal to the solution between you and this and your children, your left children, and you and your right children. So that's how I'm going to compute it. And then whenever I'm taking an element, since I know that I'm not just talking about direct ancestor, each solution will actually be computed with it left, it right, and the solution is also going to be computed with the left and the right of its children. Makes sense? To have all the combination. So this one is going to be computed with this one is going to be computed with this one is also going to be computed with this. So if you want to implement such approach, how will it look like? So you're gonna say okay, the maximum value can be equal to my helper function is actually a function is helping me to calculate the maximum difference. It's going to be the maximum difference with the left and the root, the value of this, saying that my solution is first 0, and then the right and the value of this, saying that my solution is 0. So we are going to compute the maximum of those two. Now for each of the time we are going to fall into a loop into the computation of the value. If the node is actually node, we just return the previous solution, nothing to do. Otherwise you're just going to say, okay, the maximum is actually equal to the previous solution we're having and the difference between you, that means the target we just received, and then the value of the node we just received, the target and the value of the node we just received. So at this point we have the solution in between those two. Now to continue, we are going to check if I have a right. If I have a right, I need to compute the difference in between this and the difference in between this and this, because if you are a children of my children, you are also my children. So that's why you have to compute this and this to have the differences. This is not the best thing you can do, but it is working. So you do this for the left and then you do this for the right, and at the end just return S, which is the maximum of the one of the left and the one of the right, and then the end maximum is actually the solution you have here and the solution you were having initially. If you run this, you are going to have something which is working perfectly. And then but the issue with this is that if you submit, you are going to have a time limit. And it makes sense because you are actually computing every single pair that you have in your tree. You have the time limit to the last case. And how can we solve this? How can we get rid of this? So what we can do is that at the end of the day, when you are here, you are computing the difference between this and this, and you are computing the difference between this and this. Fair enough. When you are here, you are computing the difference between this and this, the difference between this and this, and the difference between this and this. You don't really need to compute all of those. At the end of the day, when you are somewhere here, you just need to have, okay, what is the maximum of my ancestor, what is the minimum of my ancestor, and you just need to compute the difference between you and your maximum ancestor, your maximum ancestor, and you and your minimum ancestor. All those in between are always going to give you something in between the one between your maximum and your minimum ancestor. So for us to kind of apply now this new logic, we are going to going down the tree and keeping the minimum and the maximum. So we are going to update a little bit our solution in the sense of saying, okay, now I'm going to say, initially I'm going to say my minimum is the root value and my maximum is the root value. Now when calling my helper function, I'll just pass the minimum, the maximum value, and the initial solution. Fair enough. So for each of the node I'm going to be in, I'm going to say, okay, the solution here is actually equal to the difference in between my maximum ancestor and my minimum ancestor. After doing that, the minimum ancestor and the maximum ancestor, eventually I need to compare it with my previous solution. So solution 1 is this one, difference between your minimum ancestor, the difference between you and your maximum ancestor, and the second solution is you and your minimum ancestor. And then you were having a previous solution, you just need to compare the solution, the actual solution with the previous solution. This will give you solution 1 and solution 2. And at the end of the day, the solution is going to take the maximum of solution 1 and solution 2. Right? So once you have it, for each node you are going to, you need to update your maximum and your minimum ancestor. So at this point, I need to update my maximum to take the maximum of the previous maximum and the node value, and the same for the minimum. I need to update it, and after updating this, I just need to return the same logic with the left and the right. So you see, by doing this, I'm not trying to recompute this with all of the children, but whenever I'm looping, I'm just taking an element and I say who is the maximum ancestor, who is the minimum ancestor, and just make the difference in between those two, and then I'm 100% sure that I'll have the solution. No need to compute the one in between. So by doing so, I still have something which is actually working, passing all the test cases, and then let us submit and we'll see. And now this one is passing all the test casing and is performing extremely well. You can see that you have beating 100% of users C++ solution, and the memory is like not the best, right? But yeah, we are able to optimize our solution and have something more interesting and more straightforward. So this was my approach of solving this. I hope you do enjoy it. Feel free to leave me any input. I'll be really happy to interact with you regarding this. See you on the next video. Ciao.